There are two topics in this video. The first thing we'll do is take a brief look at the group S sub A, the symmetric group on a set A. We looked at this in a previous video, and one reason we want to look at this again is because it is our only example so far of a non-commutative group. And then the bulk of this module and the bulk of this video will be about subgroups. So you have studied subsystems before in your study of elementary linear algebra. You studied subspaces of a vector space. And in any future algebra course, when you look at an algebraic system, subsystems will play an important role. So let's begin with a look at S sub A. Here is a recap of the definition. So if we have any set A, then S sub A, comma, remember this little circle is the operation of function composition. S sub A composition is a group. S sub A is the set of all permutations of A, and circle is the operation of function composition. And the identity in this group, as a reminder, is the function epsilon from A to A, defined by epsilon of x equals x for every x in A. And we also know how to find the inverse of an element, say alpha of the group S sub A. If A is finite and alpha is described in matrix notation, let's try this example. We're taking the permutation of the numbers 1, 2, 3, and 4, defined by alpha of 1 is 2, alpha of 2 is 3, alpha of 3 is 1, and alpha of 4 is 4. And we want to calculate the inverse. So what goes below the number 1 in the inverse? Well, you have to look for 1 in the second row of alpha, and whatever occurs above it, 3 in this case, is the number that goes below 1 in the inverse. So for example, the number that goes below 2, I locate 2 in the second row of alpha. 1 is the number above 2. So in alpha inverse, 1 must be the number below 2, and so on. So we've done this calculation before. A little bit of new notation. So suppose the set capital A consists of the first n positive integers. Then we will usually write S sub n rather than writing S sub capital A. One reason for doing this is that our book does it, and another reason is that it's fairly standard notation. And S sub n is called the symmetric group on n elements. Let's take an example then. So we'll let A be the set of positive integers 1 through 4, and alpha will be this permutation defined by this 2 by 4 matrix, an element of S sub A, or using the new notation, this would be an element of S sub 4. And beta is the element defined by this 2 by 4 matrix. What does the identity element look like? The identity element sends 1 to 1, 2 to 2, 3 to 3, and 4 to 4. So in its matrix notation, every one of the numbers 1 through 4 lies below itself. Alpha inverse, we calculated this on the previous slide. Alpha inverse is the permutation defined by this 2 by 4 matrix. 1 to 3, 2 to 1, and so on. Alpha times beta and beta times alpha. I've done the calculations, and I'll leave this for you to check, since it's the kind of calculation that we've done several times in previous modules. Remember, alpha composed with beta means that we are doing beta and alpha in succession. We do the function beta first, followed by the function alpha. So for example, to find alpha composed with beta of the number 1, you plug 1 into beta and get a result of 2, and then you plug 2 into alpha, and the number below 2 in alpha is 3, so alpha composed with beta of 1 should be 3. And as you can see in my answer, there is a 3 lying below the 1. Here is a complete listing of the group S sub 3. So these are all the permutations of the set whose elements are 1, 2, and 3. There are 6 of these, and I want to give the table for S sub 3 and the operation of composition. So I've given each of the elements of S sub 3 a Greek letter name. Epsilon, as usual, is the identity, and then the remaining 5 elements of S sub 3 are alpha, beta, gamma, delta, and kappa. And then I calculated the table. There are 36 possible products, so I simply calculated all 36 possible products, and the result was this table for the operation of composition on S3. Some of these were fairly easy. For example, the identity times the identity is the identity, and actually the identity or neutral element times any of alpha, beta, gamma, delta, or kappa will be, respectively, alpha, beta, gamma, delta, or kappa. To take another example, here in the table is alpha times beta, right? The entry appearing in the row labeled alpha and the column labeled beta is the result of doing alpha times beta. Times is the operation of composition, and that is a delta. One thing to notice here is that taking the other order, beta times alpha is kappa. So we see in this example that S sub 3 is not a commutative group. We'll be using this convention that I've mentioned before, the convention of writing AB for A star B, if we're talking about a generic group whose operation is star. So here is a theorem we have seen before. So this is a recap, really, of what we know about groups. There's exactly one identity or neutral element in G. Every element of G has exactly one inverse. We know the cancellation laws. We proved the cancellation laws. So for all A, B, and C in G, if AB is equal to AC, the A's can be canceled. You can conclude that B equals C. This is called left cancellation, the right cancellation law. If BA equals CA, then the A's can be canceled, and you can conclude B equals C. For all elements of G, elements A and B of G, if you know that A times B is the identity, then you know that A and B are inverses of each other. And finally, in the list of items in this theorem, our formula for calculating the inverse of a product. A times B, quantity inverse, is B inverse A inverse. So the inverse of a product is the product of the inverses, but in the reverse order. And then finally, the inverse of A inverse is A. So we can take all these things as known. Two cautions, things you've got to be fairly careful of when you're dealing with groups. If you know that A equals B, where A and B are two group elements, you cannot conclude that CA equals BC. Here I've multiplied the left-hand side of the equation A equals B on the left by C and on the right by C. This is only a legal operation if you know the group is commutative. But you can conclude from A equals B that CA equals CB, or AC equals BC. You can multiply both sides of A equals B on the right by C, or on the left by C. Got my directions mixed up. On the left by C or on the right by C. The second caution is that from CA equals BC, the C cannot be canceled unless you know the group is commutative. You cannot conclude that A equals B. So feel free to use the properties of the theorem in your proofs, and I will also feel free to use them. And here's just one example. I'm going to use part 4 of the theorem, which said that if you multiply two group elements and get the identity, then they are inverses of each other. So we're going to use that to prove part 5 of the theorem, which says that the inverse of the product AB is B inverse times A inverse. So looking at part 4, it says if you multiply two group elements and get the identity, they are inverses of each other. So in order to prove part 5, I'm going to multiply AB by this thing, which I am claiming is its inverse. I'm multiplying AB times B inverse A inverse. And now I had put parentheses in, although we have agreed that it's okay to leave them out because of the associative law. But for this particular proof, I'm including parentheses. So I'm going to rearrange the parentheses using the associative law in this way. I get A, left parenthesis, B inverse, right parenthesis, A inverse. B inverse is the identity. And the identity is the neutral element, so A inverse is A times A inverse, and A times A inverse is the identity. Took a little bit of time, but I have demonstrated that if you multiply AB by B inverse A inverse, you get the identity. So these two things must be inverses of each other, which is what part 5 of the theorem says. Now we move on to subgroups. A subgroup of a group is, roughly speaking, a subset of a group which is itself a group using the same operation. This is not quite the official definition. The official definition is what I am about to give here. So if G star is a group, then H is a subgroup of G if and only if. So here's the meaning of H is a subgroup of G. There are 4 conditions that have to be fulfilled. Condition 1 is that H has to be a subset of G. Every element of H must be an element of G. H must be non-empty. For all A and B in H, A star B must be in H. H has to be closed under star. And the final condition is that for every element A of H, A inverse has to also be in H. So H has to be closed under taking inverses would be a way of restating condition 4. We use this as our definition of subgroup because this is what our book uses. So this list of requirements includes everything we need to know that H is a group using the same operation that we used on G, except for one thing. These conditions don't say that the identity of the original group, of the big group, G star, has to be in H. But this can be proved using the list of requirements for H to be a subgroup. Here's the fact. If H is a subgroup of G, using our official definition, then H is itself a group, using the operation star from G. And now the proof, all we really have to argue for is that if H is a subgroup according to the official definition, then the identity from the group G is in H. So we know by property 1 that H is non-empty. There has to be something in H. We will pick one of those things and call it A. We also know by the final requirement for being a subgroup that if you have an element of H, its inverse has to be in H. By the third requirement, that H has to be closed under star, we know that A star A inverse, which is the identity, has to be in H. So there's our proof that a subgroup under the official definition must itself be a group, using the same operation that we use on G. And now we are going to spend quite a bit of time looking at examples of subgroups. So let's start off with this question. We're taking H consisting of the numbers 1, 2, 4, and 8. And the question here is this a subgroup of U sub 15 times sub 15? So with what we currently know about groups, this will take a little bit of time to check. So first requirement, is H a subset of U15? Yes, U15 consists of the elements 1, 2, 4, 7, 8, 11, 13, and 14, and every element of H is one of these. Is H non-empty? This is an obvious yes. H has 4 elements. Okay, we're continuing with the same question on a new slide. Is H closed under time sub 15? This is the part of the question that might take a little bit of time to answer. We have to verify that if you take any 2 elements of H and multiply using time sub 15, the answer is still an element of H. And there are 16 possible ways of multiplying 2 elements of H if you take order into account. So one example, if we multiply 4 and 8, which are both elements of capital H, using time sub 15, we get a 2. Right? Remember, this is 4 times 8 mod 15, and the remainder when you divide 32 by 15 is 2. And 2 is in H. So there is one of the 16 checks that we have to do. So I'm not going through them all. I will leave the remaining 15 to you. Some are easier than others. Is the inverse of every element of H in H? Corrected a typo here. Is the inverse of every element of H in H? This also will require some time to check. H has 4 elements, so we will have to find the inverse of each of those 4 in the group U15 and verify that the inverse is still in H. Here is one possibility. 2 inverse is 8. But I know that because if you multiply 2 and 8 using times sub 15, you get 1, which is the identity element of U sub 15. So 2 inverse is 8, and 8 is in H. There are 3 other verifications that would have to be done here to verify that the inverse of every element of H is in H. The final answer is yes, H is a subgroup of U15 times sub 15. Some more examples. The set 2z of even integers is a subgroup of the integers using the operation of addition. This is fairly easy to verify. This is a subset of the integers. Every even integer is an integer. The set of even integers is non-empty. That's a requirement 2. Requirement 3, if you add 2 even integers, you get an even integer. That condition is fulfilled. And the inverse of every even integer. Well, the inverse of an integer in the group z plus, the inverse of an integer n is minus n. And the negative of an even integer is an even integer. So 2z is closed under inverses. The set of positive rational numbers is a subgroup of the positive real numbers using multiplication. So the positive rational numbers is a subset of the positive real numbers. The set of positive rational numbers is non-empty. If you multiply 2 positive rational numbers, you get a positive rational number. And the inverse of a positive rational number a over b is b over a, which is also a positive rational number. Third example, U sub 15 is not a subgroup of Z sub 15. Because U sub 15 is not closed under plus sub 15. Right? U sub 15 with the operation times sub 15 is a group. But it's a different story if we're using plus sub 15. For example, 13 and 2 are elements of U sub 15. But if you add 13 and 2 using plus sub 15, you get 0, which is not an element of U sub 15. And now let's look into the question of whether or not any of the other conditions for being a subgroup fail when we're looking at U15 and asking whether it's a subgroup of Z sub 15 plus sub 15. I just corrected one more typo. I had to add the subscript 15 to the plus sub 15 here. So do any of the other conditions fail for U15 to be a subgroup of Z sub 15 plus sub 15? So we know that condition 3 fails. In other words, U sub 15 is not closed under plus sub 15. Let's see, U sub 15 is non-empty, so condition 1 is true. U sub 15 is a subset of Z sub 15. It's actually defined to be a subset of Z sub 15. So what about the condition that U sub 15 be closed under taking inverses? Is there an element of U sub 15 whose inverse under plus sub 15 is not in U sub 15? The answer is no. For every element of U sub 15, its inverse under plus sub 15 is back in U sub 15. And here's the reason. If we take an element, a little a in U sub 15, we know two things about a. We know that the greatest common divisor of 15 and a is equal to 1. That's part of the requirements for being in U sub 15. And we know that a is not 0. So that tells us that the inverse of a under plus sub 15 is 15 minus a. I'm really referring back to a previous set of slides where we found the inverse of plus sub n and an integer greater than 2. For non-zero a's, the inverse of a under plus sub 15 is 15 minus a. So we've assumed that little a is in U sub 15, and we would like to argue now that 15 minus little a is in U sub 15. Which means we have to prove that the greatest common divisor of 15 and 15 minus little a is 1. We know that the greatest common divisor of 15 and little a is 1. If we can do this, if we can prove that the greatest common divisor of 15 and 15 minus a is 1, we will know that the inverse of little a using the operation plus sub 15 is in U sub 15. Sorry, so I'm leaving that fact for you to prove. So this means that the only condition that fails for U sub 15 to be a subgroup of Z sub 15 plus sub 15 is the fact that U sub 15 is not closed under plus sub U 15, plus sub 15. Here is sort of an example. It's an important fact anyway. If you have a group G star whose identity is E, then the set whose only element is E is a subgroup of G comma star. This is fairly easy to verify. This set will be a subset of E. This set is non-empty because it has the identity in it. It's closed under star because if you take two things out of this set, that would be, only choice would be E, and combine them using star, you will get E, which is back in the set, and the inverse of E is E, which is still in this set. So every group has this single element subgroup, which is sometimes called the trivial subgroup. And in addition, capital G is a subgroup of capital G comma star. So every group has two subgroups, and as long as G has more than one element, these two subgroups, the trivial subgroup and G itself, will be different. G is sometimes called the improper subgroup of G comma star. So for example, the set whose only element is 1 and U27 are both subgroups of U27 comma times sub 27. Oh, just a sort of a related example. The set whose only element is 1 is not a subgroup of Z sub 6 plus sub 6. The identity in this group, Z sub 6 plus sub 6, is 0. This set, whose only element is 1, is not closed under the operation plus sub 6. 1 plus sub 6, 1 is 2, which is not in this set. Here's an interesting example. We're going to let capital H be the set of integer powers of 5, 5 to the n, such that n is an integer. And we are claiming that this is a subgroup of the positive real numbers using the operation of multiplication. So as I said, H is the set of all integer powers of 5. H is non-empty. That's pretty clear. And H is a subgroup of the set of positive real numbers. Every integer power of 5 is a positive real number. If you multiply two integer powers of 5, the product, 5 to the n times 5 to the k, will be 5 to the n plus k, which is again an integer power of 5. So H is closed under the operation of multiplication. And finally, if you take an element of H, say 5 to the n, then its inverse under the operation of multiplication is 5 to the minus n. Right? 5 to the n times 5 to the minus n is 1. So H is closed under taking inverses. On to a new example. What are the subgroups of capital boldface Z sub 3 plus sub 3? Well, Z sub 3, as we know, has 3 elements, 0, 1, and 2. And we know that the set consisting of 0 by itself and Z3 itself are both subgroups. That's the trivial subgroup and the improper subgroup. And so the question I'm really asking is, are there any others? Well, every subgroup has to have 0 in it. That we proved earlier in this set of slides. So any other subgroup besides the 2 that I've mentioned, 0 and Z3 itself, will have to contain 0. That narrows it down to 2 possibilities. If there is another subgroup, it has to be either 0 and 1 or 0 and 2. But neither of these is closed under plus sub 3. Uh, 1 plus sub 3, 1 is 2, which is not in the set whose elements are 0 and 1. And 2 plus sub 3, 2 is 1, which is not in the set whose elements are 0 and 2. So what we've just argued for here is the fact that Z3 plus sub 3 has only 2 subgroups. Here's an example involving permutation groups. We are looking at the group S sub 5, so this is all permutations of the numbers 1 through 5 and the operation of composition. And the subgroup, the set we're going to show as a subgroup, is the set of alpha in S5 for which alpha of 2 equals 2. So if you thought of alpha as being in matrix form, This would be the set of all 2 by 4 matrices with 1, 2, 3, 4, 5, 2 by 5 matrices, sorry. All 2 by 5 matrices with 1, 2, 3, 4, and 5 in the top row, and with the number 2 being in the second row below 2. So we will prove this, but first I want to look at the usual method for proving that a set H is a subgroup of a group G star. The usual method is simply to argue for the 4 requirements. The 4 requirements for being a subgroup. We use the following outline. It's frequently clear that H is a subset of G. In many examples, for number 1, we won't really have anything to do. But if it's not clear, you have to prove it. You have to prove for every element of capital H that element is also in capital G. We have to show that H is non-empty. This is the second subgroup requirement. And the usual way of doing this is to show that the identity element from G star is in H. Then we have to show that H is closed under the operation from G, which is done by assuming A and B are in H, and then arguing, based on that assumption, that A star B is in H. And finally, we show that H is closed under inverses by assuming we have an element little a in H, and showing that under that assumption, the inverse of little a has to be in H. Okay, so now back to the proof in our example that H, the set of alphas in S5, such that alpha of 2 equals 2 is a subgroup. Before we actually begin the proof, though, I want to note that an object, I'm just going to call it T, is in H if and only if. So if and only if T is in S5 and T of 2 equals 2. I mean, this is the meaning of the set notation. When a set is described in this way, it means that an object is in it if and only if the object is in S5 and T of 2 equals 2 if T is the object. So this allows us to translate being in H into equations. So if you have assumed that an object T is in H, then you know that T is in S5 and T of 2 equals 2. And if you have to show that an object T is in H, you can do it by showing that T is in S5 and that T of 2 equals 2. So we'll see how this plays out in the actual proof, which we start now. So by definition, H is a subset of the group G, which in this case is S5. Right? This clause of the definition, H is the set of alphas in S5, for which something happens, tells us that H is a subset of S5. H is also non-empty, since the identity element of S5, we're calling it epsilon here, satisfies epsilon of 2 equals 2. So the identity is in H. H is non-empty. Now the argument that H is closed under the operation of function composition. Assume alpha and beta are in H. We translate that into equations. That means that alpha of 2 is equal to 2 and beta of 2 is equal to 2. And what we have to argue for is that alpha composed with beta of 2 is equal to 2, using the two assumptions that alpha of 2 is 2 and beta of 2 is 2. Well, by definition of function composition, alpha of beta of 2 is alpha of beta of 2. Beta of 2 by assumption is 2, and alpha of 2 by assumption is 2. And therefore, we have really completed the proof that alpha composed with beta is in H. And now the final part of the argument, we show that for every alpha in H, alpha inverse is in H. So we are assuming alpha is in H. That can be translated into an equation. That means that alpha of 2 equals 2. And now we have to argue that alpha inverse is in H. In other words, that alpha inverse of 2 equals 2. Well, alpha inverse, by definition, is the permutation with the property that for every x in the set of integers 1 through 5, alpha inverse of alpha of x equals x. In particular, alpha inverse of alpha of 2 has to be equal to 2. But we are assuming that alpha of 2 is equal to 2, so we know that alpha inverse of 2 equals 2 by replacing alpha of 2 by 2 in this equation. This completes the argument that alpha inverse is in H. Another example, assume that G star is a group whose identity is E, and assume that C sub 0 is a fixed element of G. And now we're letting capital H be the things in G, the set of x's in G, for which x times C sub 0 times x inverse is C sub 0. So note here that x C sub 0 x inverse is shorthand for x star C sub 0 star x inverse. And we want to prove that H is a subgroup of G star. So in this example, for any object T, T is in H can be translated to T is in G, and that this equation holds with x replaced by T, and that T times C sub 0 times T inverse is equal to C sub 0. So beginning on the proof, we first show that H is a subset of G. This is really, by definition, doesn't really require a proof. This clause of the definition, H is a set of x's in G, such that something happens, means that H is a subset of G. H is non-empty because the identity element of G satisfies the equation E times C0 times E inverse is E times C0 times E, because the inverse of E is E. And then using the properties of the inverse, that's C sub 0. This is the equation that has to be satisfied in order for E to be in the subgroup or the set H. Now, showing that H is closed under function composition, assume A and B are in H. Translating that into an equation, into equations, means that A C0, A inverse is C0, and similarly for B. B C0, B inverse has to be C0. And to show that A times B is in G, we have to show that AB times C0 times AB inverse is equal to C0. This is really the equation describing H with X replaced by A times B. So we are going to start with the left-hand side of this equation and use these two assumptions to end up with C0. So starting with the left-hand side, we have AB times C0 times AB inverse. We know that A times B quantity inverse is B inverse times A inverse. Grouping the three middle factors, we have A times B0 times C0 times B inverse, A times B times C0 times B inverse times A inverse. The expression in parentheses by one of our assumptions is C sub 0. And then A C sub 0 A inverse by the first of our assumptions is C0. We have completed the proof that A times B is in H. And finally, we show that H is closed under taking inverses. So let's assume that A is in H. That means that A times C0 times A inverse equals C0. It means this equation is true when X is replaced by A. We have to argue, to show that A inverse is in H, we have to argue that this equation is true when X is replaced by A inverse. That means we have to show that A inverse times C0 times A inverse inverse is C0. But we know that A inverse inverse is A, so what we really have to show is that A inverse C0 times A is C0. So we start with this equation, which we know is true because it's the equation that says little a is in H, and we multiply both sides by A inverse on the left and A on the right. So we're multiplying this side of the equation by A inverse on the left and A on the right, and we're multiplying this side of the equation by A inverse on the left and A on the right, which gives us A inverse A C0, A inverse A equals A inverse A equals A inverse C0A. Sorry, we're multiplying this equation by A inverse on the left and A on the right, giving this equation. And now combining the A inverse and the A, which occurs at two places here, we have E times C0 times E equals A inverse C0A. And E is the neutral or identity element, so E times C0 times E is C0. This is what we had to show that A inverse was an element of H. It's this equation with the sides reversed. Okay, one final example. If m is an integer greater than or equal to 2, then what we are going to prove is that the two-element set consisting of 1 and m minus 1 is a subgroup of U sub m times sub m. So, for example, the set consisting of 1 and 7 is a subgroup of the group U sub 8 times sub 8. Okay, so it's not completely obvious that the set 1 comma m minus 1 is a subset of U sub m. We know 1 is an element of U sub m, but we probably should argue that m minus 1 will always be in U sub m. So the first thing to note is that the greatest common divisor of m and 1 is 1, and that's what has to happen for 1 to be in U sub m. And now we want to show that m minus 1 is in U sub m, which means we have to show that the greatest common divisor of m and m minus 1 is 1. And we have proved a few weeks ago in the exercises that to show that the greatest common divisor of two numbers is 1, it's enough to show that there are integers s and t for which 1 is equal to s times the first plus t times the second. And in this case, it's fairly easy to find an s and a t that work. S equals 1 and t equals minus 1 will make this equation true. Okay, so we have the fact that we now have the fact that the set consisting of 1 and m minus 1 is a subset of U sub m. It's clearly non-empty. It has 1 and m minus 1 as elements. And now we need to show that the set is closed under times sub m. And we're going to do this by calculating all possible products of elements from this set and observing that the product of two elements from this set is still in this set. So, for example, 1 times 1 is 1, which is in U sub m. Or if you multiply 1 by m minus 1 using times sub m, you get m minus 1, which is still in U sub m. Same thing would happen if you multiplied m minus 1 times sub m1. And finally, multiplying m minus 1 times sub m minus 1 requires a little bit of calculating. By definition, that is m minus 1 times m minus 1 mod m. Multiplying out gives us m squared minus 2m plus 1. And now we're using the inserting and deleting multiples of m lemma. Inside a mod m, we're going to delete these two multiples of m. This is equal to 1 mod m, and 1 mod m is 1, which is, again, back in U sub m. So this shows that this two-element set is closed under times sub m. And finally, to show that the inverse of each element of the set 1 comma m minus 1 is in the set, we note that the inverse of 1 is 1. And this last calculation, starting with m minus 1 times sub m minus 1, shows that the inverse of m minus 1 is m minus 1. When you multiply m minus 1 times m minus 1, you get the identity. So this completes the argument that this two-element set 1 comma m minus 1 is a subgroup of U sub m.